In this video, we're going to show you how you can graph rational functions of any format, really. I'm going to lead you through a series of steps that you're going to take that will try to get you to the point where you can graph all of these with some amount of ease. So, in general, when we have a rational function, we usually are talking about some polynomial p of x that's going to be our numerator's polynomial. So just keep that in mind. When I refer to p of x in the following steps, I'm talking about the numerator, right? And q of x is, of course, the denominator. So let's make sure we keep that in mind going forward. Now, when you do these graphs, I'm going to have you go through these points kind of one at a time. Like, this is going to be your first step, and then there's going to be a second step, and then, of course, our third step. And the third step is kind of the trickiest that I think the students have trouble with, because there's kind of three different categories that you have to figure out where does this particular rational function fit. To begin with, we're going to try to plot our x-intercepts. And you know that x-intercepts are just where the graph is going to intersect the x-axis. The easy way to find the x-intercepts is by simply setting p of x, which of course is our numerator, equal to 0 and solving for x. So we're going to just set p of x equal to 0 and solve. That's going to give you x-intercepts. The second step that I would take when I'm trying to graph these is I would try to find the vertical asymptote. So the vertical asymptote is just an indication of, what is the domain value we're not allowed to plug into the function, and we can't plot a value for that x coordinate or that x value. So in order to figure out the vertical asymptote, we have to figure out where is this domain not defined. And you might remember, whenever you have a fraction, if that denominator in general becomes 0, that's undefined. We can't divide by 0. So we're going to find the vertical asymptote by simply setting q of x, of course that's the denominator, equal to 0 and solving. Now, this third step is to find our non-vertical asymptote. So I'm just going to write out this real quick. We're going to do the non-verbal asymptote. Now, you might be thinking, what does that mean? Did I just say non-verbal? Geez, I meant to say non-vertical. Holy moly, it's been a long day. So non-vertical asymptote, excuse me. And you might be thinking, well, isn't that just a horizontal asymptote? Well, it most often is, but not always. To figure out what type of non-vertical asymptote you're going to have, you have to look at the degree of the polynomial. And there's 3 different cases. So to do this, you have to look at the degree of p of x, that's of course the numerator, and q of x. And then based on that, we can figure out where we're at. If, the first case is kind of the easiest, if the degree of p of x, and just to make this maybe easy, the degree of p of x is just the degree of the top, right, is less than the degree, the degree of q of x, which is just the bottom, then we can just use y equals 0 as our horizontal asymptotes. That's really, guys, that's just the x-axis, isn't it? So if that happens, it's the x-axis is our horizontal asymptote. So that's the first one. That's the one I kind of like doing the most. Now, a little bit trickier, but not much, is what if the degree of p of x, of course that's the top, right, equals the degree of q of x. So in this case, you're looking at the degree of the top and the degree of the bottom, and they're exactly the same. The highest exponent is the same in both the top and the bottom. That means you're going to still have a horizontal asymptote. It's going to be of the form y equals a number, but it's not going to be 0. It's going to be the ratio of the leading coefficient of the numerator, right, of the top polynomial over just the leading coefficient of the denominator. Okay, so it's still going to be a horizontal asymptote. It's just not going to be y equals 0. If it were y equals 0, we'd have the degree of the top less than the bottom. The last possible case is, what if the degree of p of x is greater than the degree of q of x. So we're saying the degree of the top is actually larger than the bottom. Now, it could be that the degree is a lot larger than the bottom, but in the examples that we're going to do in this particular class, the degree of the top is only going to be 1 unit larger than that of the bottom. So for instance, for example, as we'll see in later graphs actually, if I had something like f of x equals, just to make it easy, like x cubed plus 3 over x squared, you can see the degree of the top is 3, which is greater than the degree of the bottom, 2. But it's only bigger by just 1 unit. And so when that happens, you're going to have the leading coefficient, y equal to the leading coefficient, over leading coefficient, but it's also going to be times x. So this is actually a slant asymptote. It's like a diagonal. So this is going to be a slanted asymptote. Okay, so what we're going to do next is actually apply these rules to do some graphs. And by the way, once you follow this first, second, and third step, the last thing you have to do, so let's say after you apply all these rules, you're going to simply fill out a table and plot points. So you're going to create an XY table and plot points. And that takes a little bit of getting used to, as we'll do a couple of examples in just a moment. Let's go to the next slide. So here we're going to look at a few examples. We're going to look at A together in some great detail. If you look at A, we have y equals 4 over x squared plus 1. So here's our fraction. We have a rational function. The first thing that I'm going to do is I'm going to try to get the x-intercepts, right? So for the x-intercepts, I'm just going to write x-ints. And remember, for the x-intercept, you want to just set the numerator equal to 0. So I'm just going to kind of copy that down. Remember in the previous, or up above, when you look at your notes, we want to set the numerator p of x equal to 0 and solve. So in this case, that's just setting 4 equal to 0. Well, there's nothing to solve there, guys. 4 is never equal to 0. There's no x around. It's just a plain old false statement. If that happens, that means there is no x-intercepts. So there's no place where this graph is actually going to hit the x-axis. So you might think that that's not good information, but actually that tells us quite a bit about the graph. We know it won't hit the x-axis. Let's go on to our second step, which was to find the vertical asymptote, right? So the vertical asymptote is going to occur when q of x equals 0. Well, that's the denominator. In this example, the denominator is x squared plus 1. And we're going to find when that equals 0. If I solve that, I'd have to subtract 1 from both sides, giving just x squared equal to negative 1. You might notice there's a problem, because if you square root both sides, you're going to have x equal to plus or minus the square root of negative 1, which is plus or minus I. Good luck trying to plot an imaginary number on the real x-axis, right? These are real coordinates on a real plane, so there is no vertical asymptote since it's imaginary. So no vertical asymptote. So we know that our graph is going to span or go across the entire length of the x-axis. Let's go on to our third step. Remember, the third step, if you take a look at the notes from above, we're going to try to find our non-vertical asymptote. And to do that, we have to take note of what the degree of both the numerator and denominator is. So let's actually write that down. Our degree of p of x, which remember is just means the numerator, right? The degree of p of x equals 4, our numerator in this example, is actually 0 because you could think of it as being 4 times x to the 0 power. Because of course you remember anything to the 0 is 1. So even though it's not written there, we can think of this degree is equal to 0. That's the highest exponent. The degree of the denominator, q of x, is a little bit more obvious because q of x is just x squared plus 1. The degree there is 2. So I'm going to copy that down. Degree equals 2. So now we have to think of which case that is. Well, since 0 is less than 2, that's saying like the degree of the top is less than the degree of the bottom. That's that first case. If you take a look, right, the degree of the top is less than the bottom. That means we're just going to have y equals 0 as our asymptote. And that's easy to graph. That's just the x-axis. So I'm just going to dash along the x-axis, and I hope that you do the same, to indicate that this is our horizontal asymptote. Now we have to just plot some points and get a beat for what's going on here. So I'm going to make my xy table over here since I have a little bit of space. Now I always like to start plotting points beginning with 0 as long as I can plug it in and it doesn't violate any domain issues, and it doesn't. So I'm going to plug in 0 and work outwards until I see that it's getting close to our horizontal asymptote. If I plug in 0, that means I'm going to have 4 over 0 squared, which is 0, plus 1. So I just get 4 over 1, which is the number 4. So I can plot the coordinate 0, 4, which is right there. Okay, well I'm going to plot 1. If I plug in 1, I get 4 over 1 squared plus 1, which is just 4 over 2. I get out 2. So if I plot 1, 2, that's right there. If I were to plug in 2, I would get 4 over 2 squared plus 1, which is 4 over 4 plus 1, right? 2 squared is 4, and 4 plus 1 would be 5. Now I have 0.8, right? If you put that in your calculator, that's a little less than 1. It's 0.8. So I'd plot a point there. Now you might notice what's going on here is these coordinates are getting closer to the x-axis, aren't they? Which is our horizontal asymptote. I'm going to plot one more point just to prove that to you. If we plot 3, I'd have 4 over 3 squared plus 1, which is 4 over 9 plus 1. That's 4/10 or 0.4. So if you plot 0.4, that's even closer. I mean, this is getting kind of tough to plot. Just even to go even further, if I were to plug in a huge number like 100, if I plugged in 100, I'd have 4 over 100 squared, add 1. That's 4 over 100 squared would be, what is that, 10,000 plus 1, so it would be 10,001. That's super, super close to 0. That's like almost 0, but just barely positive. So guys, as you move to the right, what's going on is these coordinates get closer and closer and closer. Oops, not a very good graph there. Get closer and closer and closer to the y-axis, but they never quite touch. So I'm just going to go ahead and finish that part of the graph going towards the asymptote like that. Now, going the other direction, I have to figure out what's happening when I plug in negative x values. Now, if I plug in -1, I think you'll notice something interesting happens. If I plug in -1, I have 4 over -1 squared plus 1. Now, since I'm squaring my x value, when I square -1, it's just like squaring +1. The same output results. I get +1. It's going to be 4 over, I get 4 over 1 plus 1, which would be 4 over 2. I get an output of 2. So if I plug in -1, I get 2. If I were to plug in -2, I'll do this one last time. If I plug in negative 2, it's just like as if I were to plug in positive 2, because since I'm squaring the x-coordinate in this case, when it's a negative squared, I get a positive. So it's going to be 4 over 4 plus 1, which is 5. I get the same output of 4/5 as I did when I plugged in positive 2. So I can get that coordinate. I know if I were to plug in negative 3, I would end up with that same output as when I plugged in positive 3, which would be about 0.4. So when I go to the left, I get values that go downwards through these coordinates and get closer and closer to the x-axis. So this is what my graph looks like. It's this kind of like hill sitting here. So that was quite a lot of work to get this relatively simple looking graph. But it's not that obvious. It's not that easy. And that's what's tough about these problems is from one problem to the next, it's not necessarily going to look very similar. They could actually, in fact, be quite different. Now, some of the questions that I'll ask you once it's graphed is what is the equation of the vertical asymptote and horizontal asymptote? And the vertical asymptote, well, there was none. The horizontal asymptote was y equals 0. My domain, since there was no vertical asymptote, I can plug in any x value in the world that I would like, and so that means it's going to be all reals. Okay? Now my range are all possible y values. Now this is not always easy. If you think about my y values, I have to kind of consider what is my top end y value, or what's the highest output I've gotten on the y-axis. And if you think about it, that was this coordinate right here at y equals 4. That's the highest the graph goes. The lowest the graph goes is like the x-axis. That's like my floor. The graph exists only in this kind of height between 4 and 0. But notice how it did equal 4. It can be equal to 4, but only strictly greater than 0. This graph never touches the x-axis. Remember, there is no x-intercept. So the way I would write my range is all y values that are strictly greater than 0 and less than or equal to 4, right? That's how we would describe all values greater than 0 and less than or equal to 4. So kind of a tricky range there. Now, I'm going to stop this video, and all I'm going to want you to do is try your best at going through all 3 of those steps and knocking out part B on your own. And then we'll take a little bit of time in class to discuss part B, and maybe we'll move on and do some more graphing together. Thanks for watching, and good luck.